An effective approach to minimize error in midpoint ellipse drawing algorithm. Abstract. The present paper deals with the generalization of midpoint ellipse drawing algorithm, MPEDA, to minimize the error in the existing MPEDA in Cartesian form. In this method, we consider three different values of h, i.e., 1, 0.5 and 0.1. For h equals 1, all the results of MPEDA have been verified. For other values of h, it is observed that as the value of h decreases, the number of iteration increases but the error between the points generated and the original ellipse points decreases and vice versa. The points will lie outside the ellipse, where x and y are real numbers. Initial decision parameter, pk, for the region R1. A midpoint ellipse drawing algorithm, MPEDA, is used to. If pk 0, then yk plus 1 equals yk and the next point will be xk plus 1, yk, which gives. Determine the points needed for rasterizing an ellipse. In this algorithm, we divide the ellipse into 4 different quadrants and each quadrant will be divided into 2 regions R1 and R2, respectively. If we are able to plot the points in first quadrant, then by symmetry we can plot the points in the other 3 quadrants. Let x, y, be the point in first quadrant, then the points in other quadrants can be determined as shown in the given table 1. Initial decision parameter, pk, for the region R2. Let xk, yk, be any point in the first region R2, then the initial decision parameter pk for the region R2 is given by. The ellipse drawing algorithm is studied by many researchers in past few decades. Some of the noteworthy work is as follows. Aiken 1 has presented a midpoint algorithm for drawing ellipses on a raster graphics display which was highly accurate and only requires a few integer additions per pixel. They have also proved and demonstrated that a simple extension of J.E. Bresenham's circle drawing algorithm doesn't guarantee accuracy in most general cases of ellipse. Hence the accuracy of the midpoint algorithm is limited only by the resolution of the display device itself, yet it requires no more execution time than the extended Bresenham algorithm. Capel 2 has introduced an original algorithm for generating discrete approximations to ellipses for display on raster devices. This approach was not new, they have combined the existing ideas to render a better algorithm for evaluating from the benchmarks of efficiency, accuracy, and elegance. Fellner et al. 3 have studied an incremental and robust algorithm that efficiently computes the best approximation of general. Let pk be the value of the function f, x, y, at the midpoint, xm. Therefore. Ellipses. Agathos et al. 4 have described an algorithm. Similarly based on Bresenham methodology known as efficient integer 8 connected algorithms for the fast algorithm introduced is higher than the existing circle drawing algorithms. Furthermore, their algorithm can be used to draw anti-aliased circles, e.g. to draw filled circle edges with different intensity, without increase in calculations. Hywen et al. 6 have proposed a hybrid algorithm for fast drawing ellipse. Dimri et al. 7 have described midpoint ellipse algorithm as one of the popular algorithms for ellipse drawing. Which gives. They have proposed an algorithm in that computes the pixels only in one octant and remaining part of the auxiliary circle. Been verified. For other values of h it is observed that as the 4 value of h decreases, the number of iteration increases but the error between the points generated and the original ellipse points decreases and vice versa. If pk 0, then yk plus 1 equals ykh and the next point will be xk plus h, yk. H, which gives. Generalization of midpoint ellipse drawing algorithm. The equation of ellipse having center at origin is given by where A and B are the semi-major and minor axes respectively and AB. The ECN, 1.1, can be written as f, x, y, equals 0, where f, x, y, equals b2 x2. Plus a2 y2 a2 b2. All points, x, y, which satisfy the equation f, x, y equals 0 lies on the boundary of given ellipse. If f, x, y, 0, the points will lie inside the ellipse, and for f, x, y, 0, the points will lie outside the ellipse, where x and y are real numbers. Initial decision parameter, pk, for the region R1. Initial decision parameter, pk, for the region R2. Let xk, yk, be any point in the first region R2, then the next point to xk, yk, in the region R2 is given by xk, ykh, or xk and h, ykh, where h is the width of the grid. Let xm, em, be the midpoint of xk, ykh, or xk and h, ykh, therefore. Let pk be the value of the function f, x, y, at the midpoint, xm. Em, therefore. Result. Let us draw an ellipse having center at 0, 0, and semi-major and minor axes are 8 units and 6 units, respectively by the. In the last entry of table 2, 2b2xk plus 1 equals 504, 2a2yk plus 1 equals 384. Thus, the region R2 begins from this point, and we will consider the point, 7, 3, as an initial point for the region R2, table 3. Similarly, for h equals 0.5 the points are found in table 4 to 5, and for h equals 0.1 the points are given in table 6 to 7. Discussion. The number of iterations depends upon the value of h. As h decreases, the number of iteration increases showed in table 2, 3, 4, 5, 6, and 7. We have solved the same problem considering 3 different values of h. For h equals 1, the classical case of MPEDA has been verified, and it is clearly shown in Fig 1 that there is a wide difference between the original curve and the curve generated by MPEDA. In the next table, i.e., table 4, we considered the value of h as 0.5, though the number of iterations increased, but the results are much closer to original 1, Fig 2. Now, we considered h as 0.1, we observed that the points are almost similar to the original curve, Fig 3.